All right, good morning, everybody. My name is Ben Manaugh. I'm currently working at CTLGroup. Today I'll be discussing the work I did for my master's thesis working under Professor Raisler at University of Illinois. I just want to acknowledge the help that Professor Henschen gave me, as well as the collaborator that we worked with on this project, Nathan Lilly at LX Construction down in Monticello, Illinois. So today we'll be discussing how we designed better 3D printed concrete mixes involving optimizing aggregates and paste volume. So going into research, if you're going to try to fix something, you have to identify what's wrong. And so with LX, a major issue for them was their section size and their paste content was leading to some pretty excessive plastic shrinkage. I mean, it's excessive if you see cracks like that. And so you're going to have to come back and patch those, and it really is just not an ideal work product, especially if you're trying to replace other means of producing wall sections. And then obviously the money in CO2 embodied in these paste-rich mixes is not ideal. We really want to bring down this paste volume. And then you'll see a lot of 3D printed concrete is not really concrete. There's no aggregates, so you're losing out on some of that restraint that would maybe help you out with shrinkage. And then obviously with no coarse aggregate or finer gradations, you'll need more paste volume to make up for that. So it's really kind of a double-edged sword there. So looking at how mixtures are designed today, or how you would go about designing mixtures, if you look at 211, maybe you want to use the pumpable or pumping concrete code 9R, you might end up at around 35% paste volume. If you're looking at 6T, for looking at your aggregate packing and designing a mix based off that, you're maybe at 30% paste volume. And then if you look at the research or the literature, you'll see extreme paste volumes, 55, 60%. And we kind of realize those are very much lab setting studies. When you look at LX Construction, our partner, and the mixes we made with them, we ended up in the low 40s or around 40% paste volume. So there's obviously some disparity between trying to use the code, use literature, and what was practical for a full-scale operation. Just some reference values for you there to kind of give some scope. And what you'll see a lot of the time in these research or lab studies is they get a lot of admixtures involved in their mixes, which are definitely essential in 3D printed concrete, I will admit that. But in our study and with LX Construction, we really used no admixtures. The focus for us was let's study gradation, let's see how we can tune gradation to get the most printable mix. And so that was our approach going in. And if you're working on mix design, you need some qualifier for mix design, just like you would have a slump cone or a flow table. We had to design our own, and so you could use something like a field vane or an ICAR or another whole host of tests. So determining what is most applicable to measuring your 3D printed concrete is essential, especially for quality assurance in the field. Looking at how we designed our mixes, we used something called the film thickness concept, which will control our yield stress and ultimately our printability. So you see here with the phase diagram on the right, you can break it down into, you have your paste-filled voids, which fill the intergranular voids in your aggregate, and then you have this sort of excess paste film, which contributes to spacing the aggregates, kind of floating the aggregates you could think of in your mix. And so you could imagine if this paste film is too thin, you'll get an unworkable or stiff mix. Good luck pumping that. And if it's too thick, you'll get segregation issues or bleeding, or you just won't get the buildability you desire. So key factors in this film thickness concept, you have your void content of your aggregate, how it packs, the surface area of those aggregates and the morphology, and then obviously how much aggregate you have in your mixture. And so you could kind of break it up into two phases here, just visually. You have your bulk, and then you have everything outside of that, which is your excess paste. Similarly, you can apply the same thing, and for us, no admixtures. So to tune your paste rheology, it's just your water-cement ratio or this excess water film thickness. So you can break it down into the same thing. And I know we would dream of getting cement to pack that nicely. It obviously does not pack like that. It's more of an analytical tool for determining paste rheology. And so when designing our mixes, first for designing your paste volume, how much you need. What we did we just set a water cement ratio that we kind of knew worked based off of quite a bit of trial and error. And then we got our blend packing density on our aggregate gradation. And then you can employ from there yield stress models. And so here's the Chateau Verlez Trung model, where you take your aggregate content as sort of your x-axis, combined with the packing and some sort of intrinsic viscosity value of your aggregates. And you can nicely plot here and predict your yield stress at different aggregate contents. Just like you can use the COT model, I'll call it, you can do excess paste film thickness as well. It just adds in another ability to tune, I should say, because you have the surface area included in that calculation. And then for our water cement ratio, which will kind of drive the printability of our mix. And obviously I already admitted, admixtures are definitely necessary for reducing cement contents and achieving, the desired rheology of your paste and whatnot. You need to, or I should say, here we used no admixtures at all. So excess water film thickness, water cement ratio, that drives these properties here. And so you can see here I've also plotted the yield stress and the excess water film thickness. And what we found was that, above 0.4 water cement with no admixtures, the bleeding was out of control, and we would get clogging. We're pumping through a 2-inch pipeline, which reduces down from a 5-inch. So it was an issue. We would get clogging quite a bit. And then if you drop below 0.33 water cement, you start to get into an unreasonable range, I would say, for the static yield stress of your concrete. You start to creep into the 3 kPa zone, which is just too stiff, I would say, for pumping and not necessary for 3D printed concrete. And so we kind of developed these windows here based off, what's stable paste and what is a necessary static yield stress for our buildable sections. And so since we're studying gradation, first we kind of have to formulate, what is our ideal gradation, which will vary from there. And so for our nominal maximum aggregate size, pumpable concrete, they say 2/5 of the minimum pipe diameter for round aggregates. For us, and you'll see this set up in a minute, when we tried to extrude our 3D printed concrete through a die with a ram extrusion, we saw that anything below, or I should say above 1/4, and we started to get clogging, every time we did the test. Where once we went below this 1/4 and we settled on a 9.5 millimeter aggregate, we never saw clogging unless it was a really just not good mix. And then for designing gradation, or at least our ideal gradation, using Funkdinger, which is really just modified Power 45, you get this packing modulus Q value, which just allows you to tune the fineness of your gradation. For concretes like 3D printed concrete or fluid concretes, you want to be on the lower end, so in that 0.2 to 0.3 range, and we settled on 0.25, just kind of arbitrarily. And then from this ideal gradation, we're going to vary it and study it, and so our variables are the fineness of the sand, so we have our 2 sands here, and that's our first variable, and then our second variable is our sand content. So first thing, just kind of an overview. This might be familiar for a lot of people, but for measuring buildability and yield stress development, there's obviously a host of methods you could use. Simplest for us, because it's extremely applicable in the field, is the field vane, which is used for clays usually. And you can see here for a 10-minute overlap time with 4-inch layer heights. First layer, we're doing okay, no collapse. Second layer, maybe still doing okay. But then third layer, we get this plastic collapse. But if you go to this 15-minute overlap time, you see there's no issue there. And it's key to identify this sort of critical time in the yield stress development between a linear growth marked by thixotropy and exponential growth marked by structuration or hydration products. And so you can see, 15-minute overlap time, no issue in that sort of open time period or before critical time, no issue afterward. But you have to remember, in this, you cannot measure with a field vane. You have to do more roundabout methods to get this curve. But just because you avoided plastic collapse, don't forget about buckling, which can be an impact you later on, even when you're developing hydration products. you could get buckling. And just to kind of show here our trend between, or the effectiveness of the effective paste film thickness variable, yield stress versus EPFT is, or provides a fairly strong linear relationship in its ability to predict. And then if you're wondering, how does this compare to our $20-some-odd thousand ICAR rheometer? Pretty good. You're getting an R-squared of 90% between this handheld tool with a much smaller sheared zone. With the ICAR, it's pretty impressive, I think, and the field vane definitely overestimates a little bit your yield stress, but it's nice to see, at least for quality assurance, the ICAR is not necessary for determining your yield stress. Despite that, of course, we ran the ICAR. You get your flow curves from that, both sort of an upsweep and a downsweep. Upsweep, you have this waiting period, so you can measure the flocculation state, which is just the hysteresis loop or the area between your flow curves. It's all beautiful stuff, but really at the end of the day, with our aggregates and our changes in gradation, the gradation had very little impact on things like flocculation state or the viscosity. It was really just this yield stress value which was impacted, and you could see, an increase in the sand content will increase the yield stress, which I think is kind of apparent with all concretes. Next, we measured lubrication layer properties to see if, what the effective gradation on that was. That left figure is kind of the development of lubrication layer on the vane, or the cylinder, I should say, as you shear it, and then the right is your flow curve. And this is all used to predict what pumping pressure you'll get in your ideal pipeline, straight line, no reducers or anything. Largely affected by paste volume, which I did not change. So it's kind of just affirmation that there isn't much of a play, or the gradation has little play in the predicted pumping pressures or the lubrication layer properties. So a slight increase in those predicted pressures with increasing sand content, but insignificant compared to changes in paste volume. Then our last rheological test was measuring the extensional flow properties and also picking up on some of the squeezing rate information with our ram extruder. And so the point here with these figures is to identify that rate is extremely important, especially when you have no admixtures or other cementitious material in your paste. Low rates, you'll get pretty extreme squeezing, and you'll see an increase in your extruding pressure. And so for us, we saw, just like in the yield stress, more sand, more extrusion pressure. When you have more extrusion pressures, you're going to get more squeezing on your concrete, more bleeding. Our final test was the forced bleed stability test, obviously it's important to have some sort of fluid migration in pumping because you need a lubrication layer, especially for plug flow. So you need to generate lubrication layer. There needs to be some fluid migration, but you can't have too much of it. Here you just see some excessive bleeding in their unsealed pipeline there. And when you get excessive bleeding, you'll get interlock, you'll get clogging, no fun. So for us to measure that, I just took the extrusion barrel and I put some back pressure on it and loaded it with a set pneumatic pressure, and then ran that through or the water percolated through a mesh, and I measured all that in a flask. And so for us, the critical value in comparison between mixtures was this initial bleed rate at 1 minute. And we saw that increasing the fineness of the sand increased the bleed rate, which may be a little counterintuitive, and I don't necessarily have reasoning for that, but higher fineness, more bleed is what we saw. So concluding, our workability, or at least our baseline workability when you have no admixtures, is really set by this paste volume or your water cement ratio. Remember, if you have too low of a water cement ratio, you'll get an unworkable mix, and too high, you'll get bleeding and clogging. We saw that the fineness of the sand, or an increase in the fineness of the sand, resulted in an increase in bleed rate, an increase in the amount of sand. We had higher yield stresses, more extruding pressure, a little bit more pumping pressure, and squeezing was a little bit more of an issue. We saw that gradation obviously had a pretty significant effect on the initial yield stress we got, but the growth of yield stress is dependent on admixtures and the cementitious you use, so gradation doesn't really affect the growth of your yield stress. It's just that initial value, that y-intercept. So overall, for developing a balanced 3D printed concrete mix, you'll need to sort of set this baseline water cement ratio to get a workable, stable paste. If you're using admixtures, maybe it's less important to set that water cement ratio to something which is workable and stable. And then tuning your fineness of your sand aggregate ratio, and paste content to just get the most buildable, pumpable, extrudable mix while still having bleed control. And so to me, what I would take away is that you want the coarsest gradation possible, which isn't necessarily true. There's limits on that. You could imagine if you made your gradation coarser, you'll have to take out some paste volume to get that same buildability, that same layer height. And so if you took out paste volume and had a coarser gradation, it may not extrude anymore. And then obviously you could get worse packing or worse surface quality with a coarser gradation. So you can't just go to a completely coarse gradation. And that is my presentation. If you want to look at Alex Construction's Instagram and see all the printing they do, there's a QR code. Otherwise, I'm happy to answer any questions. Thank you.
Thank you, Ben.